So, what if I told you that inside a simple shape, like a cube, you could hide an entire word? It sounds kind of like magic, right? Well, today we're going to unpack this brilliant system for encoding information that turns a solid block into, well, a multi-layered library. It's an absolutely incredible way to think about structuring data.
And that really is the big question, isn't it? How can one simple solid object possibly hold enough information to represent a whole word? At first glance, it just doesn't seem possible. But the solution is this beautiful, logical series of steps that we're about to walk through together.
Okay, so here's the game plan. We're going to start with the cube itself, make our first cut, and then zoom way in for a deeper dive. After that, we'll get to the real secret, the key that makes the whole thing work, before we put it all together and encode the word Mathematica. Let's jump in.
All right, part one, a cube of information. You know, before you can get to all the complex layers, you have to start with a single, solid foundation.
And this is it. Let's call it the metacube. Think of it as the entire universe for our system. Every single division we make, every bit of data we create, it's all going to happen inside the boundaries of this one shape. It's the ancestor of everything that's about to follow.
So, part two, the first division. How do you get information out of a solid block? Well, you slice it up. This is our very first move to create a kind of address system inside the cube.
And that first move gives us 27. Okay, a very specific number. So where in the world did 27 come from? Well, it's actually just some simple three-dimensional math. Just imagine making 2 cuts across the width, 2 cuts across the height, and 2 cuts through the depth. See? That gives you 3 sections on every axis. And that creates this perfect 3 by 3 by 3 grid.
And boom! Those cuts give us 27 identical smaller cubes. We'll call these our level 1 cubes. And just like that, we've gone from one single block to 27 different addresses. We've created the first layer of our data structure.
Okay, on to part three, the deeper dive. Now that we have our 27 cubes, let's just pick one of them and zoom in. We're going to do the exact same thing again, but this time with a much, much higher resolution.
And that single level 1 cube breaks down into 125 microcubes. Whoa, okay, that's a big jump from 27. So how do we get there? Well, believe it or not, we just repeat the same exact process, just on a smaller scale.
We take that one little cube and we slice it up even more finely this time. We're making 4 cuts on each axis. That gives us 5 rows, 5 columns, and 5 layers deep, a 5 by 5 by 5 grid. And these are our level 2 microcubes. So let's just pause for a second and recap. We started with 1 metacube, we cut that into 27 level 1 cubes, and now we've zoomed into just one of those and found 125 even smaller microcubes inside. The level of detail is just getting finer and finer.
Part 4, the key. Okay. You're going to want to pay close attention here, because this next idea, this is the secret sauce. It unlocks the entire system. So far, we've only been doing physical division. Now we're going to start identifying conceptual groups within the grid we've already made.
This is what we'll call a conceptual unit. So instead of slicing and dicing, we're now just looking at our 5 by 5 by 5 grid of microcubes, and we're mentally drawing a box around a 3 by 3 by 3 group. This unit isn't a new physical thing. It's a grouping that we're defining inside the bigger structure. And here it is. This is the whole game. These 3 by 3 by 3 conceptual units are not neat little boxes sitting side by side. They actually share pieces. They overlap.
Yeah. So thinking of them as separate blocks on the left, that's the wrong way to see it. The reality is what you see on the right. They're interlocked. And that is the magic key. It means a single microcube can belong to multiple conceptual units at the very same time. And that creates a much richer, way more connected data structure.
So, because of this incredible overlapping principle, we can identify exactly 8 of these 3 by 3 by 3 conceptual units hiding inside our bigger 5 by 5 by 5 grid. The easiest way to picture it, just imagine one of these units is anchored to each of the 8 corners of the larger grid.
And now for part 5, Encoding Mathematica.
Okay, so we've got this cool abstract structure, but how does this actually help us encode a real word?
Let's put this whole machine to work.
The word we're going to encode is mathematica. This is going to be our test case. We're going to see exactly how its letters can be mapped perfectly onto the queued structure we just built.
First thing we have to do is break the word down into these overlapping three-letter chunks. They're often called trigrams. So we start with the first three letters, M-A-T. Then we just slide over by one letter to get our second group, A-T-E, then T-E-M, and we just keep going. For a 10-letter word like matematica, this process gives us, you guessed it, exactly 8 trigrams. Now, for the final amazing parallel. You remember how we found 8 overlapping units inside that big 5 by 5 by 5 grid? Well, we apply the exact same logic one more time. We look inside just one of those 3 by 3 by 3 units, and we find 8 smaller, overlapping 2 by 2 by 2 groups, one anchored to each corner. And how many trigrams did we just get from our word? 8. The structure of the cube perfectly mirrors the structure of the word. It's incredible.
And this is where it all comes together. Each one of those trigrams from our word gets mapped directly to one of those final 2 by 2 by 2 groups, which we'll call syllable cubes. So mat gets assigned to cube 1. 8 goes to cube 2, all the way down the line, until Ica is stored neatly in cube 8. The word is now fully, completely encoded into the geometry of the cube.
So, there you have it. We started with a single, solid cube, and we ended up with a system that can encode a complex word. And the real genius here wasn't just slicing it up, but that incredibly clever idea of identifying overlapping groups within groups. That's what created such a rich, multi-layered way to store information.
I mean, this system is just a brilliant way to structure text. But it really makes you wonder, doesn't it? If we can map language onto a multi-layered cube, what other kinds of complex data could fit? Could you encode, say, a genetic sequence this way? Or what about a musical score? The possibilities, they're just fascinating to think about.